Hi, this is the last video for Exponentials and Logs Part 2. So in this video we're going to look at more complex contextual questions about exponential growth and decay. So these questions might involve rates, they also might involve solving equations now. So it's putting everything over the last four videos together to solve more complex questions. So here's the first one. Rabbits were introduced onto an island. The number of rabbits t years after they were introduced is modelled by p equals 8 to e to the third t. So it just says t can be anything as long as it's greater than or equal to 0. That's just because t is time and we can't have a negative time. So write down the number of rabbits that were introduced to the island. Well, if t is the years after they were introduced, then when they were introduced, t is 0. So p is going to be 80 e to the 0, which is 80. So there's 80 rabbits. Find the number of years it would take for the number of rabbits to first exceed 1,000. Okay, so t is unknown. We know p has got to be greater than 1,000. T is unknown. So what we actually need to do is solve where 8e to the third t is greater than 1,000. Okay, so we've got an inequality. So we're just going to solve that in the same way that we would solve the equation. So first of all, we need to get it in this form. So we need to make the e the subject. So I'm just going to do e to the third t is greater than 1,000 over 80. So 1,000 over 80. Which is 25 over 2. So 1,000 divided by 80. This is now in exponential form, so we're now going to log form. So a third t is greater than 25, log of 25 over 2. So t is going to be greater than, if I times everything by 3 log 25 over 2. Now I'm not going to leave it like that because we're interested in the number of years it would take. So we want the first integer that goes above that. So if I do 3 times log, 3 times log of 25 over 2, t has got to be greater than 7.57 and so on. Therefore t has got to be 8. Okay, so find the number of years it would take for the number of rabbits to first exceed 1,000. T is 8 years, or 7.57. Okay, you'd probably get away with both. Okay, part C, I'm just going to rub that out. Part C, find dp by dt. So we need to differentiate. So if p equals 80 e to the third t, then we're going to do dp by dt. So don't forget, if y equals e to the ax, dy by dx equals a e to the ax. So that's going to be 80 times a third e to the third t, and that's the derivative. Find p when dp by dt is 50. Remember, this is the rate of increase of the rabbits, so we want to know what the population is. when the rate of increase of the rabbit is 50. So first of all, we know this is 50. So we're going to say 50 equals 80 thirds e to the third t. So again, we want it in base power equals answer form. So if I times everything by 3, 150 equals 80 e to the third t. Now if I divide by 80, 150 over 80, that's 15 over 8, is e to the third t. So this is now in the right form. So I can say a third t equals log to base e, so natural log of 15 over 8. So t is 3, but times by 3, log 15 over 8. Now we've worked out what t is when dp by dt is 50. We need to know what p is. So I'm going to substitute that back into the original equation. So it's just like finding a y coordinate when you've worked out the x coordinate. So if p equals 80 e to the third t, and I'm going to substitute t into that, so it's 80 e to the power a third times 3, which is 1, log 15 over 8. Okay, now you could just stick that into your calculator, okay, but what you might notice, some of you, is if you've got something e to the log, then these just cancel each other out, like I mentioned in the previous video, and that's actually the same as 80 times 15 over 8, which is 150. Okay. So a bit more to it in terms of differentiating and then solving both the equation and the gradient function equation. Okay, let's look at another one. Radioactive decay of a substance is given by R equals 1000 e to the minus ct. So R is the radioactive decay of a substance, R is the number of atoms, T is years, C we're told is a positive constant. So there's probably a reason why we've been told that. Find the number of atoms when the substance starts to decay. So again, similar sort of start. We're working out when T is 0. When T is 0, R is going to be 1000 e to the 0, which is 1000. It takes 5,730 years for half of the substance to decay. Well, if it starts off with 1000, half the substance is 500. So T equals 5730, R equals 500. So they've given you a piece of information in order to work out what that missing letter is. So we're going to say 500 equals 1000 e to the minus c times 5730. Divide by 1000, so 0.5 or a half, e to the minus 5730c. This is in exponential form, so now if we're going to log form, so it's going to be log to base e of 0.5 equals minus 5730c. And then if we divide by that, log of 0.5 divided by minus 5730, we will get our answer for C. So log of a half divided by minus 5,730 years, which is very small. Correct to three significant figures, 0.0000121. So very small. Calculate the number of atoms that were left when T equals 22,920. So if we start off with our actual formula, R equals 1000 E to the minus 0.00121 T. That's our new formula, okay? And we can use this number in the next part because we've been asked to round it there. So the answer for this now is going to be based on the fact that we've rounded it. So we need to put in T equals 22,920, so 1000 E to the minus 0.00121 times 22,920. Very fiddly numbers. 1000 times E minus 0.00121 times 22,920. The number of atoms that will be left is 62.5. So I'm just going to leave that to three significant figures. Okay. If you wanted to round it to the nearest whole, to the nearest integer, and then D, sketch the graph of R against T. Well, it's a standard exponential decay. So sketch the graph. So we just need the first quadrant. When T equals 0, we know R is 1000. So that's 1000 there. And then as T gets bigger and bigger, this starts to get smaller and smaller and smaller. And that's what that's going to look like. Okay, there's no extra constant, so it would converge to the axis. And that's that. Okay, last question. A heated metal ball is dropped into a liquid. As the ball cools, its temperature, T degrees, little t minutes after it enters the liquid is given by that. So we've got temperature, capital T, little t is minutes after it enters the liquid. Find the temperature of the ball as it enters the liquid. So as it enters the liquid, T is 0, so big T is going to be 400 e to the 0 plus 25, which is 425 degrees C. Find the value of little t, so value of time for which the temperature is 300. So we're going to solve for little t where big T is 300. So 300, so we know T is 300, it's a little t that we don't know. So 300 equals 400 e to the minus 0.5 t plus 25. So we just need to make that the subject. So let's take off 25. And then if we divide by 400, so we're going to divide by 400, 275 divided by 400 is, what did I say it was? 11/16. So 11/16 equals e to the minus 0.05t. Okay, this is in base power equals answer. So I'll just move up here. So it's log to base e of 11/16 equals negative 0.05t. So divide by negative 0.05, and that'll give us our time. So log of 11/16 divided by negative 0.05, 7.49 minutes to 3 sig figs. Part C, find the rate at which the temperature of the ball is decreasing at the instant when T equals 50. Give your answer in degrees C per minute to 3 significant figures. So we're after the rate at which the temperature is decreasing. So it means we are going to do d big T by d little t. We want to know what that is when T is 50. Okay, so I'm just going to come down here. So dt by d little t. So it's going to be 400 times negative 0.05, which is minus 20. So minus 20 e to the minus 0.05 t. And then if you differentiate 25, you get 0. So that is the gradient function. When t equals 50, dt by dt is minus 20 e to the minus 0.5 times 50. So we just need to stick that in our calculator. Minus 0.05 times 50 is minus 1.64 degrees Celsius per minute. Okay, it's the degrees over the time. So that's why the units are like that. So it's decreasing at 1.64 degrees per minute at that instant. From the equation for the temperature T in terms of T given above, explain why the temperature of the ball can never fall to 20 degrees. Okay, so we talked about this in the second video. This is to do with the long-term effect of that model. So if we think about the model, T equals 400 e to the minus 0.05 t plus 25. Let's think about what the long-term effect of the model is. Remember, it's always to do with that bit there. So as t tends to infinity, so as time gets bigger and bigger and bigger and bigger and bigger, what's happening to this thing here? Well, that is getting smaller and smaller and smaller and smaller. That's tending towards 0. So if this is tending towards 0, then all of this is tending towards 0. Therefore, the temperature will tend towards 25 because that is what will be left. So as this gets closer and closer to 0, all of this will get closer and closer to 0, and T ultimately will end up at 25. And it's not going to go below that. So that's what it's going to tend to. So that can form part of the basis of the explanation. So the temperature will never fall below 25 degrees C. So 20 degrees C is not possible. Okay, so use this as a basis to form a conclusion about this. Okay, so remember, anything to do with long-term effect of the model, 3 parts, as 10 towards infinity, what's happening to the E, and then therefore what's happening to the overall thing. Okay, so that draws an end to Exponentials and Logs Part 2. So you should now be able to have a go at exercise 14G, where everything that you've learnt comes together in those questions.